Class, welcome to our last video in this chapter. I hope everyone's doing well. I hope that this material isn't too bad, and I hope that we all are getting ready and studying for our test coming up. Okay, so this last section, quadratic inequalities. You've actually seen some of these before. These show up when we were doing domain restrictions. So we have an idea about what this is, but we're gonna dedicate an entire section to this now. So remember, with quadratic inequalities, you cannot use the square root method. Okay, you cannot use the square root method, hence you need to factor. Okay, you need to factor. All right, so let's get some steps down. We know the first thing we're going to have to do is we need to gather everything on one side. Why do we need to gather everything on one side? Because we need to be able to factor. Okay, you can't factor unless everything is on one side. Once you have factored, what you're going to be able to do, you're going to be able to find the critical values, okay? Critical values. A lot of the times I call them boundary points. We will talk about those after we have the critical values. We're going to draw a quick sketch . And lastly, we will state the solution. All right, so let's jump into an example. I'll try to come back to these 5 steps and kind of show you what I mean here. Okay, so right off the bat, in this example, this first example, we have an inequality. We have a quadratic inequality, right? Because we see x squared. This is good. So we know that we're going to have to gather everything on one side so that we can factor. Personally, I would say I want to move this stuff on the right over to the left because I want to keep my a value positive, this 2. I want to keep it positive 2, not negative 2. So 2x squared minus x minus 10 is less than 0. All right. Now in this case, we need to factor. All right, boom, boom. If you guys want to factor by splitting the middle, that is more than okay. I know that a lot of people, when you have an a value that's not 1, you like to immediately split the middle. That's fine. Just for the video purpose and not going too far and too long, I'm going to just use my normal kind of guess and check method. I know that these two values have to multiply to negative 10. I also know that my outsides and my insides need to add to negative 1. Okay? So that means I'm going to need a 2 here and a 5 here because negative 5 and positive 4, right? Negative 5 and positive 4 make negative 1. So now I can get my critical values. My critical values, I use the same way as before, right? 5 halves, negative 2. All right, those are my critical values. So now I am done with step 3. The next thing I want you to do is I want you to draw a quick sketch. A quick sketch. And by a quick sketch, I mean pretty quick. I know that I have intercepts at negative 2 and at 5 halves. So negative 2, 5 halves. I also know that my function is opening up. Okay, so I know I'm going to have to draw something like this. All right, now the reason I do that is because now I can kind of take a look and see how this relates to 0, right? 0 is right here, my x-axis. I want to know when I am less than 0. Well, less than 0 is obviously right here, anywhere over here. And the last thing you have to keep in mind is, can it actually be x equals -2 and x equals 5/2? No, because it's just a less than sign. So you have to put open circles there. So now we combine all of these ideas together. We know that at -2 I have a critical point. It's switching from positive to negative, which is good. That's what makes it critical, is that it's switching. And then it's below, 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 all the way up until 5/2, which is another critical point where it switches from negative to positive. So I'm looking for this section in between -2 and 5/2. Now, you have two options here. -2 is less than x, is less than 5/2, is more than okay. What's the other one? The one I actually kind of like a little more, but it's not the end of the world. I'm going to go -2, comma, 5/2. And I put parentheses because I cannot include those critical points. Both of these answers are perfectly acceptable. All right, let's check out another one. X squared plus 8x less than or equal to 0. Okay, so everything's on one side already. Let's go ahead and factor this. I see a GCF. So I know that my critical values are at 0 and -8. So I sketch a quick graph. I know I have -8 and 0. And again, this is opening up. So something like that. And now this time, it says that I need to be less than or equal to 0. Well, less than or equal to means that I can be right at -8 and right at 0. But again, I want to be less than. So this area right there. So very similarly to the last one, I would go from -8 to 0. So -8 is less than or equal to x is less than or equal to 0, or -8, comma 0, and I'd have to use square brackets, okay? Okay, actually, let me use this time to kind of explain something. So if you guys remember, when we were doing restrictions, we would make a number line. It is more than okay if you like the number line method. Basically, a number line is just this picture, but it's one-dimensional, right? I can see things both in x and y if I graph a picture. If I graph a number line, something like this, and I have my -8 and I have my 0, I would know I would close it. What I would have to do is I would have to test points. So for example, if I plugged in like -2, for example, well, -2 and then -2 times 6 is -12. So that means that at -2 would be part of my solution, so I would have to shade where -2 is, if that makes sense. All right, you would have to test points if you do a number line. If you draw a quick sketch of the graph, then it's more just a visual and it's less calculations. Okay? Okay, let's keep going. Up at the top of the next page, we have something like this. Okay. In this situation, you guys can go a couple of routes. Again, a lot of the times I like to stay positive with my a value, so I would maybe think about moving these guys over. So I might write something like this. 0 is less than or equal to x squared plus 7x plus 12. Okay, and then I would go on and I would factor. What do we have? X plus 3, x plus 4. Perfect, that works. So I have my critical values. And now I could sketch my picture. So -3, -4, and it's opening up. So something like that. Not the best, but whatever, it works. And now I'm looking for it to be what? Greater than or equal to 0. Okay, I want my equation to be greater than or equal to 0. So that means when I plot my critical points, I actually want to go on the outsides of them, right? So that is one option. as well. How would we draw, or how would I write this? I would want to say, well, from negative infinity to negative 4, and I drew a closed circle, right, because it was a less than or equal to. And then I'd have to union that with negative 3 to positive infinity. Okay? Sorry, I can't show all of that right now. The screen's not letting me show it all. But yeah, if I draw this and then I need it to be greater than or equal to 0, right? I want it to be on above 0, then I would have to sketch and shade in those two sections of the graph. I do want to actually take some time. What if I moved the 12 over? Okay, what if I moved the 12 over instead? So we're going to do this problem a second time. And we have negative x squared minus 7x. And then this time I'm going to move the 12 over here. So now it's less than or equal to 0. Okay? Well, I would start this the same way, but I would need to factor out a negative. And then I could factor x plus 3, x plus 4 is less than or equal to 0. Okay, so I still get the same critical values, which is pretty cool. When I go to sketch this, however, what is different? Well, I still plot my critical values. But now what's happening? What's happening? Now my a value is negative, right? So this is opening down. This is a parabola opening down. So I'd have to sketch something like this. All right. And then now I want to be less than 0. If I want to be less than 0, so now I'm here, and again, I would have to sketch where it's less than 0. Okay, so at the end of the day, you get the exact same answers, which is neat, right? Whichever way you do this problem, you get the same thing. It's really a matter of preference. Again, I'm more of the type that wants to keep my a value positive no matter what. Some people like to keep everything on the left side. They like to keep this the 0 on the right side. It just makes more sense to them. It's kind of up to you. Okay? All right. Now, let's move on. I know I'm getting a little lengthy here. All right, so solve x times x minus 7 greater than 8. All right, now this kind of looks factored, right? It looks like it's already in factored form. There's a big problem, though. There's a huge problem, actually. When we factor, the whole reason that we factor is so that we can use the zero product property. The zero product property means that this number has to be a 0. Because this is an 8, this means nothing to me right now. This does not help me whatsoever. I am not ready to do anything. Okay? If this were a 0, you're good to go. But it is not a 0, so we are not good to go. We actually need to clean this up. We need to move the 8 over to the other side. So before I even do that, I want to distribute this out. X squared minus 7x, and now I can move my 8 over, is greater than 0. Hopefully that makes sense. The whole reason we use factoring is because we know that when you have something factored and it's equal or greater than or equal to 0, whatever, well, one of the pieces is going to have to be 0. But when it's an 8, well, I don't know anything about the two pieces. They can be absolutely anything. Okay? So now we can factor, let's see here, x and x. I'm going to go minus 8 plus 1. Right? Got to get to negative 7, so negative 8 plus 1. Perfect. Critical points of negative 1 and positive 8. So we sketch them. Negative 1, positive 8. And my a value is positive, so I'm opening up. Something like this. Just a quick sketch. And now I say I need to be greater than 0. So at negative 1, at 8, I have to put open circles because it's just greater than, but then I'm going to shade wherever I'm greater than 0 or above 0. So I now know that I need to shade to the left of negative 1, to the right of 8. So when I combine those ideas together, I should get negative infinity to negative 1, parenthesis, because I do not include it, and then I skip to 8 all the way to positive infinity. All right. Oh, we have another one where it kind of looks factored but not really helping us. We need to clean this up. So I'm going to distribute out this 2, so 4x squared minus 6x plus 9, all greater than or equal to 0. Okay, I distributed, I moved the 9 over. Let's see what we can do here. Okay, in this case, when I have a 4, I think I'm going to maybe try the A and C route, see if I can split the middle. So 4 times 9 is, so I have to multiply to 36 and add to negative 6. So MA. 1 and 36, no. 2 and 18, no. 3 and 12, no. 4 and 9, no. 6 and 6, no. I'm really struggling with this one. I can't figure out what multiplies to 36 and adds to negative 6. Guys, when you don't get it right away, one thing you could always do is you can check the discriminant. Let's see if it's even possible. So when I check my discriminant here, which is b squared minus 4ac, I'm going to do what? Negative 6 squared minus 4 times 9. Alright, so 36 minus 16 times 9. Ooh, I can already tell this is going to be negative. So that means what? No critical points. There's not going to be any critical points. Okay? Now, that doesn't mean that we're done, there's no solution. It just means that there are no x-intercepts for this function. Okay? We still want to try and graph this. Let's think about this for a second. We know that there can be no x-intercepts. We also know that it's opening up. It has a y-intercept of 9, so maybe I can plot that. I mean, really, I can graph something like that. How do I know that it's something like this? Or, again, it's not perfect, but it's a sketch. There cannot be any x-intercepts because the discriminant was negative. Okay, so now when I look at this, my picture, and I say greater than or equal to 0, well, that's going to end up being everywhere. Okay, so my answer here should be negative infinity to infinity, or all real numbers. Okay? Alright. Again, if you can't figure out how to factor something, check the discriminant. See if something's messed up. More times than not, if you are feeling good with your factoring and you can't figure out how to factor it, well, more times than not, the discriminant's going to be negative, which means there's no critical points. Alright, now, one kind of extension question, or not really extension, but something we've done before, and we can now kind of think about it in a new way, is this domain. We remember that what? An expression under a radical has to be greater than or equal to 0. So, negative 5x squared plus 7x must be greater than or equal to 0. Now in this case, I'd probably just take a GCF, right? I can definitely take out an x, which would leave me with negative 5x plus 7. And now I could do a little bit of work here. Actually, you know what? I'm going to change this just because it makes a little more sense to me. I'm going to make this positive, make this one negative. Okay, so now I have my critical points at 0 and negative 7/5. Okay. No, I did that wrong. If I factored out a negative, I'm sorry guys. Let me redo this. Sorry. Negative x means I would have 5x minus 7 greater than or equal to 0. So my critical points would be 0, and positive 7/5. I'm very sorry about that, guys. Okay, so now that we're back on track, I have 0, I have 7/5. I know what my a value is negative, so I'm opening down, something like this. And I know I need to be greater than or equal to 0, so I'm looking from here right to there, which means my answer would be 0, 7/5. Okay, so last thing we're going to do, we're going to go over a little bit of testing of discriminants just so you guys can kind of see what's going on with some of these other examples. All right? So, first thing we're going to do here, we're going to calculate some discriminants. So, b squared minus 4ac. So 5 squared minus 4 times 2 times 9. 25 minus 8 times 9. Okay, I already know this is negative. Alright. The second box is the exact same, so I'm just going to already write it's negative. Alright, this is different, so now I'm going to have a negative 4 squared minus 4 times 1, or what? 16 minus 16, so I have a 0. And, okay, calculate discriminant. 4 squared minus 4 times negative 3 times negative 11. So 16, well, negative 4 and negative 3 would be positive 12, but I still have this negative 11. So once again, this is going to be negative. And then, of course, if this one's going to be the same thing. Okay. So now when we graph our quick sketches, and we can do all of these axes like right now. I just went ahead and I drew my axes. What do we know is going on here? Well, I have an a value of 2. Sorry, you can't see where I'm pointing. A value of 2, which means it opens up. Y-intercept of 9, something like this. Alright, I know it opens up, so I could do something like that. And of course, these are the same picture, so I'm going to just draw the exact same sketch. Now over here, what's happening? I have an a value of 4, so it's opening up. Maybe a y-intercept of 1. I mean, the other thing that you have to keep in mind here is that because the discriminant is 0, it has to just touch at 1. It can only have one x-intercept. So I'm going to sketch something like this. Alright. Now the last two, the only thing that is different about the last two pictures is that now my a value is negative, which means it opens down. And again, it still can't have any x-intercepts. So now my sketch would look something like this and like this. Okay, now the reason we're doing this is because I want to show you how this kind of changes when we put this into an inequality type of situation. So we take our original, so 2x squared plus 5x plus 9. If I want it to be greater than 0, let's go greater than or equal to. If I want it to be greater than or equal to 0, well, where is this picture greater than or equal to 0? Everywhere, right? So this is negative infinity to infinity, or all real numbers. What if I change? What if I want it to be less than or equal to 0? It doesn't happen. It can't, right? It cannot go below the x-axis. Now, this middle one, what if I take this this equation or expression 4x squared minus 4x plus 1 and I turn it into an inequality saying greater than or equal to 0? Well, it's greater than or equal to 0 here, here, here. It's equal to 0 right there, and then it goes back up. So once again, this is everywhere, or all real numbers. And now for the last two, negative 3x squared plus 4x minus 11 is greater than or equal to 0, or less than or equal to 0. All right. Where is this graph greater than or equal to 0? Nowhere, right? It's all below. It's never above. So that is a no solution situation. Where is it less than 0? Well, similarly to our very first box, this is always below the x-axis. It's always below 0. It's always negative. So here we would say negative infinity to infinity, or all real numbers. Okay, so this was just some practice on sketching pictures, figuring out our quadratic inequalities, how to solve them using our quick sketch method. All right, I hope everyone has a nice day. I'll see you next time.